So what are trees? Trees are essentially a special case of undirected graphs. So when we say a graph is a tree, first, if it is connected. Second, if it has no simple cycles. So a tree is a connected undirected graph with no simple cycles. Here are some examples. For example, G1. First, we need to check if G1 is connected, and if G1 has no cycle, then it is a tree. So what is the definition for connectivity? We say a graph is connected if every two vertices are connected. And when two vertices are connected, we say two vertices are connected if there is a path between them. And if you check all these vertices, every vertex is reachable from other vertices. So it is connected. And by looking at the graph, we will see that also it does not have a cycle. So G1 is a tree. Now for G2. Again, we need to check connectivity. And if you see that there is a path between any two vertices, so every two vertices are reachable, so it is connected. Is there a cycle? Obviously that we cannot see a cycle on the graph, so G2 is also a tree. Now, however, for G3, notice that here we have a cycle. So since it has a cycle, then it is not a tree. However, it is also connected. So see that every two vertices are connected, but since there is a cycle, so it is not a tree. Now for G4 we cannot find any cycle, but in fact if you look at the graph, this forms one component with two vertices, and also this will form also another component, isolated component, so the graph is not connected. Although it does not have any simple cycle, but since it is not connected, so G4 is also not a tree. So when a tree is said rooted tree, now this one is not a rooted tree, and also this one is not a rooted tree. A rooted tree is a tree in which a particular vertex is designated as the root. So we pick any of these vertices and make it as the root, and then you draw all other adjacent vertices below that root. To demonstrate on how to draw a tree as a rooted tree, we are going to use G1. So this is our graph now, and if we want to draw the graph as a rooted tree, then we have to pick one of the vertices as the root. Now, for example, suppose that now the root is f. So we will pick f as the root. So we will put f in a level. So we will draw the tree in levels from top to bottom. So we will put f in the first level, and since f is adjacent to two vertices E and C, so we have to put E and C in lower level. So I will put here E, and here we will put C, and there is an adjacent, and they are adjacent, so there is edge between them. Now next we go for the other vertices. Now for E, it does not have any adjacent vertex, so we will stop it here. And now for C, it is adjacent to three vertices. So we have to draw in lower level three vertices, and one will be for D, and one will be for B, and one will be for A. So now the root, this is the root. So G1 is drawn now as a rooted tree. Now what if we select another vertex as the root? For example, let us select D. And now since D is only adjacent to C, so we will draw C in lower level than D. Now C is adjacent to other vertices than D, F, B, and A. So these are the three vertices adjacent to C. So we will draw C. Below it, we will draw three vertices. One will be for F, and one will be for A, and one will be for B. Now F is adjacent to E, so we will draw E in a lower level. When you draw vertices in the next level, if we have only one vertex, so you can just simply draw it below its parent vertex. But if you have more than one, then you can distribute them so that you make a space for the drawing. We will go over some definitions on a rooted tree. So here we will assume that T is the label for the tree and the root is V0. X, Y, Z are just simply vertices on the tree. And suppose we have the following path, V0, V1 up to Vn, which is a simple path in T. And I have given here as an example of a tree. And see, for example, V0, V1, V2, V3. This is a path. And Z, Y, X are vertices. Now we need to define a level. So what's a level? You have already seen how to draw a rooted tree. If two vertices are adjacent, then one will be drawn in a level, and then the one next to it will be in a lower level. In this sample tree, so this is level 0, and this is level 1, and this is level 2, and this is level 3, and this is the deepest level of the tree. Now, how to find a level of a vertex? Suppose I would like to see what is the level for X. Then find a path from the root to that vertex. So this is the path, and count how many edges do we have in this path. Now, since we have 2 edges, then this is at level. So X is at level 2. Now, suppose I would like to know what is the level of V3. So find a path from the root to that vertex and count the edges. So we have 3 edges. So this is level 3. Now, the height of a rooted tree is the maximum level. So the maximum level is level 3. So the height will be from here up to here. This is called the height of the tree. Now, for any adjacent vertices, for example, V1 and V2, and remember that in a rooted tree, 2 adjacent vertices exist in different levels. So one of them will be in one level, the other one is in another level. So if V1 and V2 are adjacent, so the one on top level will be the parent of the one that is in a lower level. And the one that is in the lower level will be a child to the vertex in the upper level. Now, if we have a path, let's say from the root until we reach a certain vertex, which is V3. Now, all vertices on the path except V3 will be ancestors of V3. So V3, the ancestors of V3, V2, V1, and V0. See, these like all grandfathers of a person in a family tree. Now, if you look at it from the root, if you go to V0, V1, V2, up to V3, then V0 will look all of the vertices on the path until V3 like grandchildren, and they are called descendants. So V3, V2, V1 are descendants to V0. Now, if we have 2 vertices, they share the same parent, then they say that they are siblings. And finally, a vertex with no children, for example, these, they are called leaves. So we have 1, 2, 3, 4, we have 5 leaves in this sample example.